As we discussed in our introduction, harmonic analyses are used to determine the steady-state response of structure to loads that vary sinusoidally with time. This enables the verification of a design, providing insights such as will resonance occur, which this could result in excessive motion, stress, noise, and vibration. Will the cyclically repeated load result in repetitive stress, resulting in fatigue damage and potential failure? So, dynamics problems can be solved in the time domain or the frequency domain. So let's take a closer look. In the time domain, the input and responses are arbitrary. For example, here we have an input that rises to a peak and then drops to zero. This would be like hitting a part with a hammer a single time. We would then expect the response in the structure to maybe vibrate, as we can see here. We also are typically investigated and interested in the transient response, or how that response changes over time. We can see the response is cyclic, but with a decaying amplitude. Also, it should be noted that to reach a steady-state response is computationally expensive, as we have to solve for the transient response. Multiple iterations are required to get to the steady state. Now, on the other hand, in the frequency domain, the inputs are sinusoidal. So we solve for the response for a particular excitation frequency using one solution iteration. We then repeat these solution iterations as we sweep over a specified frequency range of interest, solving for the steady state response. We can have multiple excitations, but they are all steady state sinusoidal. Now, the harmonic function is comprised of three main variables. In this case, the forcing function f sub I is comprised of the excitation frequency omega sub I, the amplitude f sub I, and the phase angle theta sub I. If we substitute in a given time t, we can compute the force. Now for a little more details. For the imposed circular frequency omega, it's equal to 2 pi times the imposed frequency, which is given in cycles per second. The frequency f is the inverse of the period t sub f. The amplitude is the peak of the forcing excitation, and it acts in both the positive and negative directions equally. The phase angle on the forcing function is typically necessary when there are multiple loads present, as to control their relative phase or timing. Again, substitute any time in the equation and we can compute a resulting applied force. Now we'll take a moment to talk about complex variables and notation, which are very helpful when we get to the derivation of the equations. Why do we concern ourselves with complex variables to begin with? Well, they are somewhat abstract. Their use facilitates the mathematics of the solution. While it is beyond this course to fully explore complex variables, we will touch upon the necessary fundamentals and use this complex plane Argand diagram for reference. A complex variable z is shown as a vector in the plot and can be written as shown where x is the real part of z, y is the imaginary part of z, and I is the imaginary number, or the square root of -1. Now, from the Argand diagram, we can see that from simple trigonometry that if a is our amplitude, then the real part x is just a times cosine phi, and the imaginary part is just a times sine phi. So depending on the angle phi, we have varying real and imaginary quantities. The animation phasor plot shows the trace of the real portion cosine of the function. Notice how it is an oscillatory steady-state behavior, smoothly transitioning from max to min. Now, complex variables can be written in two common forms: the exponential form and the trigonometric form. While the trigonometric form intuitively illustrates that the function has a sinusoidal shape as shown previously, the compact, mathematically equivalent, and elegant exponential form will be used in the equation derivations. But it is worth keeping in mind the equivalent trigonometric form because it is more intuitive at times, especially when mentally visualizing harmonic motion. While we have discussed force and displacement, other quantities of interest include the velocities and accelerations. So far, we have just discussed the force and displacement. We know from our studies in physics the following. That is, velocity is the derivative of the displacement, and acceleration is the derivative of the velocity. Now recall that displacement in harmonic motion has real and imaginary components. And recall, these are sinusoidal. So too, we will expect velocity and acceleration to have the same sinusoidal form. If we differentiate our complex displacement, we can derive the complex velocity and acceleration. For mathematics, specifically the derivative of the exponential function, we end up with the same form, but now we just have the function modified in the amplitude and the phase, respectively, by the forcing circular frequency omega and the imaginary number I. So to visualize this, let's momentarily revert to the trig form of the equation. Let's plot these on the graph. We have normalized the amplitudes to 1 for the example, just to make the graphs easier to compare the phase shift. Here we can see easily how a harmonic steady-state response varies over time. Notice how the velocity is shifted to be 90 degrees out of phase with the displacement. When the displacement is at a maximum or minimum, the velocity is 0. Also notice how acceleration is shifted 180 degrees out of phase from the displacements, or 90 degrees from the velocity. Additionally, when the displacement is at a maximum, the acceleration is at a minimum, and vice versa. Now that we have the necessary background, let's get back to our equations for harmonic response. Starting with the matrix form of the governing equations of motion, let's explore a harmonic solution to this equation. We state that the forcing function f and displacement u are of this form, which is no surprise as we know the harmonic excitation response will be sinusoidal in nature. Recall that these complex functions can be visualized as sinusoids, and simply given the value of t and circular frequency omega, we can compute the complex values of the force or displacement at each node, once we have of course solved for the unknown max values and phase shifts for each node in the model. We differentiate the displacements to get velocity and acceleration. We substitute and simplify, resulting in the harmonic equation of motion. This equation can be solved directly using what is called the full method, using the full matrices, and these are coupled equations. But as we stated in the section on mode superposition, we can use the M-sub technique or mode superposition method to gain efficiencies and still maintain accuracy. Now we won't be able to cover in detail all the steps in the derivation, but using the mode superposition method equations and some more math, the equations can be converted into modal form. Recall the modal form of the equation has the complex modal coordinates y sub jc as the unknowns, which are fewer to solve than the previous physical degrees of freedom as unknowns. It is computationally efficient to compute since the equations are uncoupled, only one dependent variable per equation. From the mode superposition method, we then compute the displacement contribution from each mode, and let's call this C sub j. It is formed by solving for y sub jc and the mode shapes or eigenvectors phi sub j. Finally, we compute the complex displacements u sub c by summing over the n modes. We use curly brackets to indicate that c and u are vectors since our model will have typically many nodes. Please see the section on mode superposition method if necessary, where we introduce the basis of this method. A few points can be made by looking at the modal coordinates equation. When the excitation frequency, uppercase omega, is equal to the natural frequency, lowercase omega, and the damping zeta is equal to 0, then the modal coordinates y sub jc is infinite. Now in a physical system, exciting a structure at the natural frequency or resonance, when uppercase omega equals lowercase lower omega, this may happen, but there should always be some amount of damping in the mathematics to prevent predicting a non-physical infinite response. In addition, when exciting at the natural frequency or resonance, the phase angle of the response is 90 degrees from the input. We will discuss this in more details in the next section. Now, as discussed prior, The output from the harmonic solution is the complex displacement vector. This provides the real and imaginary values of the results at all the nodes. But often a more useful form of the results are the amplitude and phase. Recall from the discussion on complex notation relationship, where x is the real value and y is the imaginary value. We can therefore compute the amplitude of the steady-state response, which is typically more useful than knowing the real or imaginary results, because a structure's response will be a combination of the real and the imaginary. In one way, the real and imaginary can be thought of as the portion of the amplitude at a given time based on the angle as we saw in the phasor plot during the discussion on complex notation. As we march along in time, the quantity omega t is changing, resulting in different values of real cosine omega t and imaginary sine omega t. These are the components of the displacement. The phase angle result will allow us to determine how much the output, such as displacement, velocity, or acceleration, will lead or lag the input, or if it is in sync with the input or other loads. Now, up until now, we have discussed the results quantities of displacement, velocity, and acceleration. But as we have seen in the other sections, the strains are derived from the displacements, and the stresses from the strains, and the constitutive model, of course. In this case, let's assume linear elastic materials like Hooke's law. It is often of interest to understand the harmonic sinusoidal stress levels, as these will be repeating at known frequencies, and using these results, fatigue damage and life predictions can be made. Finally, while the stress and strain components, like the normal and the shears, are harmonic sinusoidal, popular derived quantities like principal stresses or equivalent stresses are not.